Hey everyone. So today we are going to learn how to solve for the output of the match filter, and this is the first video in the solving for the output of the match filter series. And today we're just going to in this video, we're just going to kind of go through a little overview of just different things that we're going to look for and eventually solve for. But the first thing that we actually want to look at in this process is actually just look at the equation, which I am writing everything on the board. But the equation for the output of the match filter is um, it's y of t, and y of t is equal to an input signal s of t convolved with the impulse response to the match filter, h of t. And just to note that this h of t, the impulse response to the match filter, it's also known as the impulse response to a filter matched to the input signal s of t. So those terms are used fairly interchangeably, and we actually will learn how to find h of t from s of t by just inspecting the graph, and that will be covered more in the next video. But to continue along with this equation of the output of the match filter, y of t, one of the properties of convolution is that it's commutative. So that means that y of t can also equal to h of t convolved with s of t. And to take it a step further, we will actually, in one of the methods that we'll be using to solve for the output is we want to put this in integral form. And in integral form, it takes on the form of negative infinity to positive infinity of s of tau h of t minus tau d tau. And using that commutative property, we also can say that it is the integral of negative infinity to positive infinity of s of t minus tau h of tau. Actually, let me just undo this a little bit so that it looks a little bit nicer. Um, h of tau d tau. So that's what the output of the match filter will look like. Is it takes these forms. So we have that convolution integral. And so the second thing that we're going to do, and I will write it down, is we actually, in order to be able to use these formulas, is we want to be able to get an equation from this graph of s of t. So we want to write s of t in terms of unit steps. So that's going to be number 2 is write s of t, and I'm writing all of this down in unit step form. And from s of t, we will actually be able to find h of t, because h of t is it's the impulse response to a filter that is matched to the input. So number 3 on our list is going to be find um, h of t from s of t and write in unit step form. And lastly, the thing that we're going to do is we are going to, and I'll put it up here, is we're actually going to solve. And there are 3 methods of solving for the output, and I'll write them down. The first method that we're going to use is the analytical method, or like almost like numerical analysis. So the analytical method, which we will actually use this convolution integral, and we're going to use the unit steps that we'll get in steps 2 and 3. We're going to use those unit steps to actually define the limits of integration. So it's very important that we learn how to write the equation in terms of unit steps, and that's how we will solve the analytical method. And in the second method, we have Laplace transforms. So we have Laplace. And then the last one is the one that everybody really loves, and that is the graphical convolution method. So graphical. And in the next video, we will dive into how to write our input signal S of t in unit step form. So stand by for the next video.